All good? Okay, so the key object I'll be interested in is, so it will be given by different sets of enumerative invariants. Of log Calabi-Yau surface pairs. X, D. And initially I'll be interested in a relatively restricted subset given by so-called Neff Loyenga pairs. So what's the setup? So X will be a smooth, rational projective surface, or the complex numbers, and the toolkit will be an anticanonical divisor. Is this corner here visible? Hopefully not. So this will be an effective singular anticanonical divisor given by the union D1 through to DL of singular simple normal crossings divisor, where I will require that each irreducible component Di is smooth and Neff. So in particular, since I'm requiring D to be singular and each irreducible component to be smooth, I'm requiring this divisor to be reducible. And so I'm not allowed to use these two boards, right? So the prototypical example will be given by, well, for X we can take the projective plane, 2. And for D, the union of a conic and the second line intersecting it at 2 points. So think of the board to be the projective plane. I got a conic and the line intersecting it. And the kind of, so when I say enumerative invariants, the sort of questions that I have in mind have, well, the following flavor. I may be interested in, well, there are enumerative questions. There's some kind of count of curves. So a plane curve is specified by degree D polynomial into variables. It's specified by a set of its coefficients. And I want to impose some constraints on these coefficients that fill the geometry of this divisor, as well as on the interface. So one thing that I want to impose is a nonlinear condition on the parameters of this degree D polynomial. I want to impose that the curve is rational, at least for starters. So this imposes a bunch of constraints by the degree genus formula. And there's another set of constraints that I want to impose by Bezout theorem. The intersection of this degree D curve with the line will be generically at D points, fundamental theory of algebra. Likewise, on the conics, the intersection will be generically at 2 D points. And I'm interested in the maximally degenerate situation where these points coalesce into a single point of maximal contact order equal to the intersection multiples, which is D, well, D and 2D respectively. So maximally tangent at a unique point on the line and a unique point on the conic. And some counting off the number of degrees of freedom shows that there's one leftover degree of freedom that I want to kill off by imposing a point condition, so that my curve passes through a point in general position of the plane. So I've got a picture like if I fix a point, I want to look at curves of degree d. There are tangent at one point at the line and one point at the conic. And what I said, there's a zero-dimensional space of those. There's a finite number of configuration, and the question is, what is this number? Through one point in general position. So this has a very classically looking, almost high school flavor in terms of at least the possibility of drawing pictures. And the physics will happen one dimension higher. And for me, the physics will be mostly something that will drive, an intuition that will drive methods of proving mathematics. This will be in complex dimension 3. And the key object I'm interested in here will be a set of, protected observables in a topological subsector of the type 2A, a non-gravitational type 2A compactification on the Calabi-Yau. I will consider some special Lagrangians in some Calabi-Yau 3. And I'm interested in the open and closed topological A-model amplitudes associated with those. To have a simple example in mind, which will be related to the board above, think about toric Lagrangian A-branes on the vertex. And to give away the punchline, there's a board on its own. What I'm going to show in the talk is that there are several enumerative invariants of curve counting type of very different flavor from one another. They are attached to an F-flowing pair X and D. And even though they're different, somehow the physics intuition, as well as some other type of guidance, will lead me to show that they are nonetheless all related. And moreover, there is a closed form solution to the calculation of all these invariants. So sometimes we can compute all the invariants that I'm going to be talking about in 2 minutes. And from this closed form solution, confirm the expectation that they are related in a predicted way. Sometimes we can prove that they are related, and even though they are not all closed form solvable, it would be sufficient to solve just one enumerative theory to rule them all as well. And so this is based on joint work with Pierre Bousseau and one of the organizers, Michel Van Garel, and with another project with Marcin Yannick, who's in the audience, as well as on ongoing work in progress with all three of them. In this work in progress, which I'll advertise at the end, I will show how I can relax essentially most of the adjectives, condition that I put on my divisor. Consider it general, as general as possible. Okay, 10 minutes into my talk, I guess the talk can start. So, okay, I said there are, what kind of curve counting theories will I be interested in? So to me, curve counts will always mean parametrized curve counts. So I will be mostly considering Gromov-Witten type invariants throughout my talk. And I want to consider curve counting invariants that simultaneously fill the geometry of the ambient space, the ambient surface X, and the divisor. And I'm going to consider two examples that fill this geometry in a very different way. So the first set of invariants are the local invariants of the pair, X and D. So what I'm going to do here is I will use D to define the embedding of my surface into a higher dimensional Calabi-Yau variety, which is a rank L vector bundle on the surface. So associated to the pair X and D, I will consider the total space of the direct sum of the dual line bundles to each irreducible component, di. So this is net rank pair. This is OX minus di. This is a 2 plus L dimensional quasi-projective variety, and since D is anticanonical, this total space is Calabi-Yau. And in scare quotes, my first set of invariants is local Gromov-Witten invariants, and 0 log D, will be some sort of count of degree D genus 0 curves in this total space that pass through an appropriate number of points, which is L minus 1. Points on the surface. Now, as a scheme, the moduli space of maps to this target space is the same thing as the moduli space of maps to the base, just the moduli space of genus 0 maps to the surface X, because of netness. So a holomorphic map to this total space is not allowed to wander off from the 0 section, so long as the map intersects non-trivially, or is generic, it intersects non-trivially all of these divisors. But the respective obstruction theories differ, and there's a virtual fundamental class, which, at least in the simple case of X equals P2 or P1 cross P1, realizes Richard's fantasy on the first day of this workshop. So the difference in this obstruction theory is encoded into a canonical obstruction bundle on the moduli space of maps to the base. And the virtual fundamental class is cut out as a top-term class of this obstruction bundle. And virtual dimension in all degrees is equal to n plus L minus 1. And now if I want to remove the scare quotes in the second line, what I can do is I can pull back by evaluation maps L minus 1 points conditions to this moduli space and integrate against the virtual fundamental class. So these invariants really are I can take L minus 1 pullbacks of point conditions on the surface and integrate against log 0, L minus 1, and D. So if you're not too familiar with this, just think that this thing can be given a rigorous mathematical construction in algebraic geometry. These numbers are often non-enumerative, as is known in, already from the case L equals 1, Calabi-Yau threefolds. But the Calabi-Yau world is somehow special. Especially in mirror symmetry, and the fact that I'm looking at non-compact Calabi-Yaus like this opens up avenues of calculation of these invariants by localization. So they're non-enumerative but easy in a way, easy-ish. And there's a second set of invariants that I want to associate to the pair, and these are those that relate more closely to the example that I made on that board. So instead of looking at ordinary Gromov-Witten invariants of an allied space, this total space of the direct sum of O minus di, I can compute, well, I think I have to keep the scare quotes, the number of degree d genus 0 curves in X itself through L minus 1 points. They are maximally tangent at each reducible component di. Now there's a whole host of additional complications related to the situation, particularly in regards as the construction of a compact moduli space for these objects. There are various tools on the market to deal with this, and perhaps the chief tool to deal with this in the case in which our divisor is singular is to use log geometry. So I can consider the log Gromov-Witten invariants of X and D, viewing X as a log scheme for the divisorial log structure induced by D. And the corresponding numbers, N0D log, they will be constructed by, instead of capping against this virtual fundamental class, I will consider a different moduli space, well, the moduli space, the Abramovich-Chen-Gross-Siebert moduli space of basic log stable maps. With maximal contact conditions, X, D. And again, this is a proper dilemma for stack with the perfect obstruction theory and the virtual fundamental class, which, as in the previous case, has virtual dimension n plus L minus 1 for all degrees. And if I want to compute these numbers, once again, I can pull back L minus 1 point conditions and integrate against this virtual fundamental class. So geometrically, this is a completely different situation. In one case, I was counting curves in a big, non-compact, higher dimensional Calabi-Yau of dimension higher than 3, strictly higher than 3. In the other, I'm doing curve counts in the surface, but with some incidence condition at a bunch of divisors that intersect transversely. And although these, and unlike the previous invariants, the local invariants, these are very often enumerative, but they're much harder to calculate. So somehow their status is exactly opposite. Yes, I have.
So for the virtual load section, is there a explicit description of the structure level that you put?
It's the first higher direct image of the push down from the universal curve of the pullback of the normal of X inside E of XD. So you
push forward the first.
Yeah, so you have the universal curve on the moduli space M0n XD. And you have an evaluation map of X. You can pull back the normal of X inside E of XD, so that vector bundle that disappeared, by F, If you take R1 push forward of this, that's a vector bundle on this modified space, and you take a top-chain class. So a fiber over a fiber over a smooth modular point is just H1 of pullback of under your stable map of this direct sum 4 minus di. No, so Nefness is what takes care of this. So that's the statement of Nefness is exactly that. You only have this H1 to care about. That you do have a genuine vector.
And then now you have a different moduli space.
Exactly. Yeah.
And there's no obvious or any morphism.
Well, you could forget about the log structure, for example, and you can push down the. Well, you can ask yourself, what is the relation between the push forward of this virtual fundamental class and that top chain class of the instruction bundle that I had?
But there's nothing a priori for getting the universal log structure for pulling back.
No. Everything here. So on the log side, you don't see the bundle. That's what I'm going to say next. Well, the answer. Well, is there any expected relation? Not by me. So these invariants are very different geometrically, but a mixture of phenomenology and staring at the degeneration formula for long enough, led people to the following conjecture. So this is a conjecture of Van Garel, Graeber, and Ruddat, Chirka 2017, is that these invariants are essentially the same thing. Up to some universal factor, which is some sign factor, -1 to the L, the number of components, the product of the intersection multiplicities along each irreducible component, and I guess I have an additional sign. And the first thing that I want to tell you today is that, so this conjecture is a theorem. So this is Busseau, myself, Van Garel, for Neff Loenga pairs. And moreover, both sides are closed form solvable. Martha?
Sorry.
Was that for me?
I'm liking your dog for once. So can you come with the lesson you wrote me?
Sorry?
What is closed form?
Okay, so there's a formula. There's not an algorithm. There's not a recursive formula. There is an actual formula. There's an explicit generalized hypergeometric function that you can feed with combinatorial data describing your pair, and that gives the answer. And I'm just going to sketch the proof. Well, the ideology of the proof. Right? I'm being a bit slow. Probably that's why. That's why you like it, right? Okay. So this is going to go down here from here. Sorry, this is my glass. Okay, I'll pause. So the strategy of Sorry?
Is this the first relation you want invariants?
Yeah. So the first one was conjectured by Takahashi in the late 90s, circa 2000, and proved by Gopakumar in the case of P2, relative to a smooth divisor. The body of evidence was enlarged by Graeber-Hassett in the case of the Petze surfaces relative to a smooth anticanonical divisor. And then I presented that as a conjecture, but Michel, Tom Graeber, and Helge Ruda have a proof in the smooth case, which led them to conjecture that the same could hold in the singular case. So the timeline is like 98, mid-teens, and then 2007. Sorry? No, there's nothing open yet. Okay, so the proof, the key of the proof is a degeneration argument in Gromov-Witten theory. And as the number of components increases, so that the divisor gets more and more singular, the difficulty in making an explicit comparison between the virtual classes or the enumerative invariants also increases. No, I knew that. That's fine. But somewhat paradoxically, the invariants are easier to compute. So this suggests a divide and conquer approach, where for number of components greater than 2, one can calculate the invariant. And find a closed form. So on the log side, this is done through some version of tropical correspondence theorems, relating this to tropical Gromov-Witten invariants. And on the local side is using techniques in local mirror symmetry. And the good thing about higher dimensional Calabi-Yaus is that mirror maps become trivial pretty quickly, and they're always trivial in dimension higher than 4. And once you have all the invariants, you can ask yourself, do they satisfy the predicted relation? And that's the case. Whereas for L equals 2, it turns out to be easier to find a direct comparison statement for the invariants, as the explicit calculation of all the Gromov-Witten invariants is out of reach. And although the Gromov-Witten invariants are hard to compute, the local ones are much easier to compute. Once again, one has like explicit hypergeometric expression from mirror symmetry up to a mirror map that miraculously is closed form invertible by algebraic functions. So the calculation of the local invariants and the equality lead to a calculation of both the log and the local invariants. So yeah, maybe I can make just as an answer to the original question, in the case of X being the projective plane and D the union of a line and a conic, the specialization of this mirror symmetry formula, which reproduces a localization calculation of Klein-Pandari-Pande, has the form -1 to the D divided by 2D squared times 2D choose D. And plugging this into the formula tells us that the log invariants of P2 line and conic are equal to, this is just a prefactor, the sort of junk that we had in the comparison, they are equal to the central binomial coefficients. And this is the answer to the problem that I had at some point before. Small n subscript. So there's a general solution, and the theorem holds. And this will be the end of some talk. But it's a solution that creates way more problems than it solves.
So this is more like the original
Right, indeed. Exactly. There's some massaging that you need to do because you get a singular space when you do the generation on normal cone. There's some singularities you need to solve, to resolve, and then the original degeneration formula doesn't apply because you're in the log set. So you need to use the Abramovich-Chen-Gross-Siebert decomposition formula. But the same sort of miracle that you have like vanishing up to one particular curve degeneration type occurs in this case. No. No, I mean, you could, but it actually turns out to be cheaper to do this. And so what are the problems? And, well, there's one natural question that one can ask, which is what happens in higher genus. So far, I've only looked at genus 0. So what about higher genus? And let's start by looking at the log side of things. Now, you can consider genus G, degree D, log Gromov-Witten invariants. Well, the typical thing that you do in Gromov-Witten theory when you go to, or of surfaces, when you go to higher genus, is your virtual dimension increases linearly in G. And the way to make up for that is you have to consider like extra insertions to get a finite number. This is what you do for, say, the higher genus Gromov-Witten theory P2. There's another operation that you can do to sort of what the physicists would call soak up these extra zero modes, which is you can consider the same type of insertion, pulling back L-1 point conditions. And this lacuna of G in the degree can be filled by considering the top-chart class of a canonical rank G vector bundle on the modulus space, which is the Hodge bundle. C-top of Hodge bundle. So the fibers being the space of holomorphic differentials on your curve. And this is something that you can define. And something else you can define is some generating series for these numbers. N twiddle Q. So this is a formal power series in a variable log Q squared. And it's defined in this way. And what is the value of this? Well, Rousseau in his thesis has shown that the tropical calculation that lead to determining the genus 0 log Gromov-Witten invariance can be upgraded to a Q-deformed tropical calculation of this higher genus log Gromov-Witten invariance parametrically in this parameter Q, giving you the all genus answer in one go. So knowledge of N0D log, at least the method of calculation of N0D log, can be upgraded to a calculation of this all genus generating functions in Q. And the key idea is to promote tropical multiplicities to their Bloch-Gölsche counterpart. So their Q analog. So here, Q analog of an integer n. It's a symmetric version of the usual Q analog. Q analog minus Q minus alpha. So in particular, whatever you could compute in genus 0 on the log side can be upgraded to a calculation of all genus Gromov-Witten invariants with this lambda class insertion. Like the usual scattering calculation is promoted to a quantum scattering calculation with wall crossing functions being Q deformed in this way. And the final result is also Q deformation of the genus 0 result. Like instead of having the central binomial coefficients to D choose D, you have their Q analog. And okay, that's one side of the story. And there's the previous comparison between log and local invariances remains a little bit unbalanced. The natural question is what happens to the local invariants in higher genus? So what about higher genus? Ordinary Gromov-Witten invariants of these non-compact Calabi-Yaus. And well, the question is a non-starter because the virtual dimension decreases linearly in the genus and becomes negative as soon as the genus is at least 2. So there's not even a set of higher genus Gromov-Witten invariants on the local side that you can play with. So if you want to resist the temptation of ditching this whole story completely, you can get to the following proposal. And the proposal is that these local Gromov-Witten invariants are not really the right object to look at in this comparison. And what they really are is, so this answers Lotte's question that I'm happy to answer in absentia for now, is that the local Gromov-Witten invariants of, or if you want the genus zero topological A model of a Calabi-Yau n-fold, is really the open topological A model, the open n-3-fold Gromov-Witten invariants of a Calabi-Yau threefold. Okay, this is not a completely. Okay, I want to argue that this is not a completely crazy proposal. So first of all, for n equals 3, this is tautological, which is a good start. The second sort of geometric guiding principle is that all these relative stable maps are really a limiting object, can be thought of at least as a limiting object given by some open stable map with boundaries adding on some Lagrangian near the divisor, with a connected component of the boundaries winding around circles on these homologically non-trivial circles on this Lagrangian. And so these Lagrangians are designed to, they should bound a holomorphic disk emanating from the divisor, and in the limit in which you push the Lagrangian against the divisor, you swallow up your disk, your holes close into punctures, and your winding numbers translate into compact orders for your relative stable map. And now it turns out that at least for n equals 4, this is a realization of the physics idea of Petermeyer in the late 90s. There's a well-known story of relating the cross-partition functions of 4 and 5 dimensional gauge theories to the topological string on a Calabi-Yau 3. You can try and ask yourself what happens if you go 1 dimension higher, and what kind of F terms the topological string will compute on a Calabi-Yau 4-fold. And so Green, Morrison, and Plesser show that this type of codimension 2 insertions compute some effective superpotentials for n equals 2 theories. And the same type of F terms can be engineered as D4 brane superpotentials by Guru and Vafa by considering instead D4 branes wrapping around certain Lagrangians, which is the set U. Now, in a special case in which the same superpotential can be realized in both ways, both as a War volume theory or as coming from an effective theory from a higher dimensional Calabi-Yau, then you have a mathematical relation between the respective invariants. Okay, there was a lot of propaganda and ideology, so let me try and write some formulas now. So what's the idea? So this is the first instance where physics can guide us towards the answer. I'm really sorry. So you start with your Loyenga pair, D1, DL. Always think about the plane with the line and the conic, if that helps. What you can do is, you can consider the complement in X of the first L-1 of these components, and consider the total space of the restriction of O minus dl on this, on the complement of all these di's. So this is it's a quasi-projective Calabi-Yau threefold, and in this threefold you can consider Lagrangians near the divisors in the surface and consider a real section of this vector bundle, or a real subbundle of this vector bundle, fibered on this Lagrangians. So this will lead to special Lagrangians on this Calabi-Yau tree, which I'm going to call Y. And under very lax conditions, when XD is an F-Loinga pair, so I'm just going to bury all this condition into this small asterisk over here. I'm very happy to explain what they are. The corresponding toric Lagrangian pair, YL, the corresponding special Lagrangian pair is an Lagrangian-Vafa. On some toric Calabi-Yau tree. So an example of the plane with a line and a conic, you can remove a line and take a twist on the complement of the line, which is A2. That's just C3 with one toric Lagrangian. Now, what's the benefit? Well, there's an algebraic geometric theory of open Gromov-Witten invariants for this toric Lagrangian pairs, by using the extra structure that we have, namely the fact that we can use localization. In particular, there's a construction of a virtual fundamental cycle in all genera, MG0 bar of YL, of virtual dimension 0 in all genera. So I'm going to integrate one of it. And I can arrange those into some generating function, the same way I did it before. So this is the Taylor coefficient of order 2G of some formal Taylor series in a variable log Q. And so now we got something that, by what I said before, this higher dimensional geometric engineering is designed to match with the local invariance as Q tends to 1, which is the genus 0 limit. So it agrees on the nose with the local invariance, and it's defined at all general. So we've got something to put on the right-hand side of this. And so the statement that we may hope to be true is that if I replace my Lagrange-Witten invariants with their all genus generating functions with top lambda class insertions, these are going to be equal to this higher genus open Gromov-Witten invariants, which refine to all genera the local invariants, up to some factor. And the expectation for this factor is that whatever deals with the Lagrangians is untouched. And when it comes to the twisting, it follows from an application of a paper of, Pierrick, Honglu, Messier, Guo, and Wu, that the natural prefactor should also be Q-refined. So we have an additional sign factor for the divisor we twist by, and we take the Q refinement, so the Q analog of its intersection multiplicity. And this is a theorem for an F Loinga pairs. And moreover, both sides are closed from the solvable. The proof is an application in itself, so let me start by talking about applications. So it started at 35, and haven't I? Got 15 minutes. 0. This here. Okay, let me start. So what are the consequences of this log open principle? Well, the method of proof is a comparison of the formula for the higher genus, well, cutiform quantum scattering for calculation for the log invariance with a topological vertex calculation for this open invariance. So you have a formula on the left-hand side and you have a formula on the right-hand side. But it's not the same formula. So the proof is an application in itself. This is something that Yannick highlighted at the end of this talk on Monday. Got something that is a very wild multivariate hypergeometric expression for this log invariance, which is predicted by this principle to be equal to some compact product of Q binomial expressions from topological vertex. So there's a non-trivial combinatorial statement that one can make, which leads to a closed form resummation for the higher genus log invariance. And so the topological vertex is already an application as a method of proof. Now, there's a whole lot more that we know about this open invariance of toric Calabi-Yau threefolds than we do about the log invariance. So one thing that we know is that, well, there are higher genus techniques for from the local B model mirrors, the Gopakumar-Vafa mirrors to these, using topological recursion. There's an integrable hierarchy in work of mine with Rossi, Carlo, and Romano, which is a reduction of 2D Toda, which computes these invariants. There are a bunch of statistical models, like matrix model and crystal models with defects, that compute these invariants and that reproduce the same closed form solution. So this is all very computational, and moving to something more conceptual, that there are other invariants. I did say several invariants, one can attach to the pair, which are conjecturally related to the actual curve count in the higher dimensional Calabi-Yau in the local situation, genus 0. So Clement van der Ripande defined higher dimensional Gopakumar-Vafa invariance through some multi-covering formula. So mu here is the Möbius function, and there's some multi-covering factor of q to the 4 minus L. So this is a definition. You're just defining a sequence of rational numbers. And conjecturally, these should be integers. But now, there's another set of BPS invariants that one can consider by the same multi-covering formula applied to the open invariants, and these were considered by Labastida, Marino, Oguri, and Vafa in the context of open Gromov-Witten theory. Large n duality for non invariants of well, the open invariance in genus 0 for the corresponding toric pair. And the first corollary of the log open theorem is that, well, in genus 0, these invariants are exactly equal on the nose to the local invariants, almost by design. And the left-hand side are defined in terms of the same multi-covering formula. Therefore, they're the same. And if you are pragmatically minded, you can ask yourself, what's the gain in establishing this equality? Well, there's a lot more that we know about this Oguri-Vafa invariance than we know about this Clement van der Ripande invariance. And this is the second input of well, recent progress in physics. For L equals 2, we know that these BPS invariants on the right-hand side are computed by, well, they coincide with the Donaldson-Thomas invariance of a certain symmetric quiver. It's an instance of the Knox-Quivers correspondence of Kucharski, Sulkowski, Stosic, and Reineke. So there exists a symmetric quiver, Q, depending on X and D, such that, well, the absolute value of this KP invariance is equal to the absolute value of this LMOV invariance by the previous point, which is equal to the Donaldson-Thomas invariance of the quiver. by a theorem of Efimov, we know that the latter are positive integers, or non-negative integers. And this establishes the conjecture claim on the integrality for all these local surfaces as a one-line corollary of the local principle. As this generalizes beyond L equals 2, I'm just going to mention it very briefly. Marta, you okay?
Yeah.
Okay.
It lost me about 10-15 minutes ago.
That's okay, now you're back.
That's it.
Okay, I'm just going to mention briefly that this generalizes to all dimension and number of components higher than 2. And in fact, it applies to a refined integrality for the higher genus Gopakumar-Vafa invariants. And moreover, so this addresses a question that I think Mainz asked Jockstock at the end of his talk. Has anybody tried to compute this for DT invariants of fourfolds? And in fact, in this specific case, well, not in this specific case, but yes, in genus 0, the DT invariants for L equals 2 of this Calabi-Yau fourfolds were conjectured by Tzal to coincide with this KP invariance. And there were explicit checks by Tzal Monavari. Okay, in small degree, which uses input this local calculations on the proof of the previous theorem. And to conclude, there's a lot of statements that one can make, and that I've made throughout this talk, but what I haven't said is that they apply to this XD net Lowenka pairs, and I haven't told you how many of these exist in nature. So how constraining is it that I have an anticanonical divisor with a singular anticanonical divisor with some decomposition, and I'm imposing netness on each reducible component. I can take X to be a toric surface, D to be the toric boundary, which is anticanonical, and I require what do I get if, so how many toric varieties out there satisfy the fact that each reducible component is net? Well, the answer is that you have P2 and P1 plus P1. That's it, just product of projective spaces. When you don't consider the toric boundary, you get a lot more, but it's still a finite number of smooth deformation families. So can we do, there's not a lot of X and D out there the way I presented it. So what about generalizations? And that's what I've hinted at the beginning of the talk, that I wanted to relax a bunch of these conditions. Like the first one you can think of is, what about smoothness of X? Can I consider something that is like Waterstein singularities? So what about orbitals? And by and large, all I'm going to say is that everything I said holds true upon replacing variety with the Lie-Markov stack. So, for example, you can consider like X to be the weight of the projective plane, and D some singular divisor that passes through the point with one component that passes through the point with Z at stacking list. It's a quiver, an open geometry, and all the statements carried through. That gives already an infinite number of examples. You can play with the order of your singularities. And perhaps most interestingly, I want to get rid of netness altogether, which, the way I've presented it seems kind of a non-starter. I said it, in order to define the local invariants and to have a compact moduli space, I was requiring that each irreducible component had precisely in response to Tyler's question. But instead of imposing positive intersection as a condition on the divisor, I can impose it as a condition on the degrees of my stable maps. So I can look at non-net examples and just restrict to, for example, stable maps such that the image lands on the net cone. That's a full dimensional subcone with pseudo-effective cone. And all the statements should make sense. Now, there are up to blow-ups on either the nodes or smooth points of the divisor, there are three minimal series for L equals 2, 3, and 4. They are parameterized by an integer. In case n equals, so a non-negative integer. N equals 0 is nef, and then you have a whole tower of non-nef cases. So for example, for L equals 2, you can have xd with x the nth Hirzebruch surface. I'm also giving up of nefness of the anticanonical altogether. This can be greater than 2. And d, the union of the curve with self-intersection n, and a smooth representative of the linear system generated by the other toric divisors, the curve with intersection n and the two fibers. And what we're showing in this work in progress with Pirek, Michel, and Yannick is that this whole local open business carries over. And the reason for that is that the ideology of the proof is solid under this non-net modification. So in the calculation of the invariance for more than two components, the triviality of the mirror map and the finiteness of the scattering on the log side remain true. So you just have an extra parameter floating around from which you can deduce the comparison. And in the proof we gave, the comparison statement we made for A equals 2, the condition of nefness did not intervene at all. You just had to impose positive intersection with a divisor. So that remains true. And so what you have is a calculation giving you a comparison, and a comparison which hopefully can give you some way of calculating things. And that's the final thing that I want to say. In the net case, both the open and the local invariants give you closed formula. In the non-net case, the log calculation becomes basically impossible in terms of complexity. It's a case in which one has not only infinite scattering, but entire sectors where each wall gets activated at some point for degrees long enough, for degrees high enough. The local calculation, which was manageable, is using, well, Coates-Giebenthal type theorems, is not manageable anymore in this non-net case. The reason is that although the I function lies on the Lagrangian cone, it's no longer, it doesn't have the same h bar asymptotic expansion of the J function. One has to, as a Laurent series, and one has to extract the J function by Birkhoff factorization, which you can do degree by degree, and as before, you have an algorithm, not a formula. And what wins you everything here is the fact that there's an amazing algebraic closed formula for the open invariance, which, since you've established the equalities, gives you a closed formula for the log and the local invariance in one go. And this is the third instance of physics input in this talk, this generating function turns out to be the planar resolvent of the chiral part of Q-deform two-dimensional Young-Mills theory on a two-sphere, which was considered by Hagenagich, Oguri, Salini, and Vafa in the context of Z black hole, Oguri's Strominger-Vafa conjecture. And if you can smear out entirely the physics motivation, and you can cut to the chase and find that the topological vertex expression can be expressed in terms of some matrix model, which, and the physics literature starts being rigorous from that point on, can be solved rigorously in the planar limit by giving you some singular integral equation that can be solved by matrix model techniques. And so this computes all these invariants for all these net cases. And final thing that one could ask is, well, this is just a resolvent. It's a planar piece of a generating function of say Wilson loops. What about the partition function itself, the planar partition function? Is there any interpretation for that? And it turns out that this solves the remaining constraint that I put, which was the fact that my divisor was irreducible. You can ask yourself, I can have a singular divisor, and I can have that be irreducible, like a twisted cubic in P2. What is the solution? You have exactly the same problems for the log and the local side. But the free energy of the matrix model will compute the invariance for this irreducible singular divisors. And I think I start at 35. I can stop here. Thank you.
Going back to the dark side of blind did you use one invariance?
Yes. I don't have an answer to that.
You have an answer?
No, I don't.
No, you don't.
Because you're also changing the type of insertions. That, yes, you have genus 1 invariance, but you don't have a point condition anymore. So it's quite different. I've got nothing to say. It's probably not something that fits this picture. More questions?
What is there? So this formula that you were that you using over, what's the relation between that formula and the energy document?
Sorry, what formula are you thinking about specifically?
It was the one the higher genus version that was involved to.
Oh, the comparison formula.
Yeah.
Yeah, okay. Yes. Okay, you can, I guess you can already ask that question at this level, because in that case, since it's irreducible, you're looking at local theory of a surface in threefold. That paper has a comparison formula for the higher genus local invariance and the higher genus log invariance in any dimension. Then, when you specialize to the case in which you're considering a smooth del pezzo, then you know that the output of the formula is that the higher genus log invariants are controlled by the higher genus local invariance and the Gromov-Witten theory of the elliptic curve. Then something that you can try to do is, instead of considering smooth del pezzos, smooth projective surfaces, you can try to look, for example, as quasi-projective surfaces with invariance defined by localization. And in that case, the effect of the decompactification, if you will, which is what we're doing in this case, is that instead of having the Gromov-Witten theory of the elliptic curve and in the coefficients of the polynomial expression of the log invariance in terms of the local, you have the Gromov-Witten theory of P1. So you have a bunch of integrals of like lambda classes on MGN bar, and if you sum them to all general, that's the Q refinement that you get. So it's a massive simplification of that formula in this restrict.